we introduce our work on 3D reconstruction, learning to generate dense point clouds with textures on multiple categories. 3D reconstruction from single RGB images has been a long-standing challenge in computer vision. While recent deep learning-based techniques have made significant progress, the reconstruction of detailed geometry and texture for a large variety of object categories and complicated topology remains challenging. Recently, several works proposed to train neural networks to reconstruct shapes from RGB images. Prior work chose volumetric grid mainly because its grid structure is convenient for 3D convolution, but the memory grows cubically. Point clouds are close to raw sensor data, but point-based methods often rely on fully connected layers, resulting in an output with a fixed and limited resolution. Recently, implicit functions have also been used to represent and generate high-resolution shapes, but post-processing such as smashing cubes are required to extract surfaces. In contrast, our method represents 3D shapes with multiple 2D views, so we can take full advantages of 2D convolutional networks and generate higher resolution point clouds. We propose a two-step pipeline to generate 3D points from single RGB images by first predicting partial shapes from the input, then completing the shape and texture. Our pipeline consists of 4 modules: 2D RGB image to partial shapes, joint projection from partial shapes to multiple views, multiview texture and depth completion, and a final joint fusion. The first step is to predict a partial shape from an input color image. We propose to use the 3-channel object coordinate image to represent the partial shape. Each pixel of the object coordinate image represents a point in 3D space. With this image-based 3D representation, we formulate the 2D to 3D transformation as an image-to-image translation problem, which is handled by the U-Net-based 2D 3D net. Since the object coordinate image is aligned with the input image, we can easily acquire texture for the partial shape with joint texture and shape mapping. The second step is to project the partial shape into multiple depth and texture maps with joint projection, which is a differentiable operation. We use a set of depth maps and texture maps from 8 different viewpoints to represent the partial shape. After we extract multiple partial views, we formulate the reconstruction problem as a multiview completion problem. In the third step, we propose a multiview texture depth completion net, MTDCN, to jointly complete the partial texture and depth maps. We also train MDCN, which only completes the partial depth maps and generates more accurate results. Here, we show an example of completing the 8 partial texture and depth views. The completed texture and depth maps are fused into a colored point cloud. Since we use multiple 2D images as shape representation, our network can generate very dense point clouds. We train our network on 13 ShapeNet categories and test it on novel objects. Compared with baseline methods, our point clouds are not only denser but also textured. To see how our approach generalizes to real-world images, we evaluate the ShapeNet trained model on Pix3D. First, we consider the case of reconstructing real-world objects from scene categories. We test the methods on 3 categories: chair, sofa, and table that are in the 13 ShapeNet training categories. Even on real-world data, our methods generate dense point clouds with reasonable textures. In the second case, we reconstruct real-world objects from 7 unseen categories. This figure shows qualitative comparisons. Our method produces reasonable structure for beds, desks, and bookcases, while the baseline methods take them as sofas and chairs. Our outputs also recover more details like the curved legs. Now we show the quantitative results on the Pix3D dataset. Our method outperforms the baseline method in mean chamfer distance with or without ICP alignment. We compare the 6D pose estimation accuracy of different object-centered reconstruction methods by calculating the average closest point distance. Our method outperforms 3D LMNet on all test datasets. We also compare the relative improvement of chamfer distance after ICP alignment. Compared to 3D LMNet, the performance of our methods relies less on ICP, which implies better pose estimations. Thank you for watching.